Right, welcome to the Higher Combined webinar, where we are talking today about P1, part 3, well, part 3 and 4, and I'll explain that in a minute. Before I start talking about any of the science, I do want to talk about the fact that you may or may not yet have had an email or a letter home about coming to collect some resources from school. Now, it's really important that you wait until the date and time in that letter that you to come to school. Please don't turn up at a random time, say Mr. Lamb said there were things for us to collect, because you're not allowed. And if you haven't got your letter, don't worry, they're going out, people are obviously coming in at different times, and none of it is till next week anyway. But for all of you that are doing the higher tier, we have put out some questions, or we will have put out by the time that you are due to come in, some questions from Exam Pro on some P1 topics, along with the mark scheme at the end, so that you can test yourself on the topics that we're talking about. This one happens to be about what we're talking about today, the particle model of matter. Okay, so as well as that, if you have bought a combined science revision guide, you've already bought it. Don't rush on to parent pay now, because it's too late. If you've already bought one, then that is out in your place as well, just to let you know. Right, let's get started on a little bit of the science. Now, Miss Wanstall is here today so that she can answer your questions as we go past. So Miss Wanstall also teaches the higher tier sets as well. So hopefully you're going to get lots of answers today. Now, what I'm going to cover today, I'm going to mention the particle model of matter. In fact, I just held up some questions about that and said there are some out there for you to collect and do. So after half term, you can do some paper-based activities instead of everything being a Google quiz or slides. I'm not really going to talk about it because it's quite a simple idea. There's solids, liquids, and gases, distribution of particles in those, the energy used to break the bonds, and density. Okay, they're fairly simple ideas. If you click on this link here on the slide, which is in your Google Classroom, there are 7 videos in there about the particle model of matter and density and the required practical. The required practical, if you're not sure, the density required practical is the one that used this can. Filled it with water, probably made a terrible mess, water came out, you measured the volume, then you put it on a balance and you were able to work out the density using that. If you're not sure about that practical, because you haven't revised it, you're not sure about the particle model of matter, solids, liquids, and gases, and what happens as a solid becomes a liquid, and that the energy is being used to break those bonds. If you're not sure about any of that, watch these videos, okay? It's quite simple, and I think that all of you will be able to get that by watching that video. So I'm not going to spend time going over that. So I'm going to talk a little bit, briefly, maybe 10 minutes. I'm going to talk about the structure of an atom, isotopes and ions. And before you all scream, but that's chemistry, sir. Yep, it's in C1 as well as P1, so it's really important. Then we're going to talk about the model of the atom. You're screaming, that's in chemistry as well, sir. Yes, it is. It's in both, so it's really important to know it. But I'm going to go through it reasonably quickly, because mostly what I'm going to talk about is radioactive decay and nuclear equations. Okay, that's what we're really revising today, but it would be silly to do it without having mentioned atoms and ions. The particle model of matter comes in front of this. Okay, so solids, liquids, and gases and how they behave, and density. And if you're unsure about any of that, go back and watch those videos.
So just to double check, are they still going to have the option to do the online work if they don't want to come in and pick up the papers?
Absolutely. The coming in and picking up the work is because some students had said that they would like to have their books. That was originally what was happening, is some students had said, we would really like to have our science books. They're full of revision things. We'd rather be making notes in those. So there is a possibility for you to come in and get them. There is no compulsion whatsoever to come and pick anything up. You do not have to come to school. However, if you want your books and you want something to write on, if your teacher thinks that it would be useful for you, they have put that out on your table. I know that all of the students I teach, I have put questions out for them and their books. If you want them, you can come and get them. I'm not going to think badly of you if you don't come and get them. You might be very happy just doing the stuff online, but some people aren't. So we're trying to make it possible for you to do both. Okay. And again, please don't come in until you get an email telling you you can, okay? Because they're very strict, going to manage which tutor group comes on which day and at what time. Okay, right. So just a quick bit about an atom. You need to know about protons, neutrons, and electrons. And if you don't, this is something you need to go away and revise. I'm not going to reteach it here. I'm just telling you that when we get on to looking at radioactivity, if you don't know that the nucleus contains protons and neutrons, and that the electrons are in energy levels or shells around the outside, then this all gets a little bit difficult. This is stuff from C1. Again, so protons have got a charge of +1, electrons -1, and neutrons don't have a charge. And we say the relative mass, protons 1, neutrons 1, and electron we generally give as 0, but 1/2000th. So there are some questions here for you to test yourselves and some definitions. It's really important you read those definitions and that warning, because often in the exam, people would write, or on tests, people write the definition of the atomic number incorrectly because they say it's the number of protons and electrons. Even though they are the same number, the definition is it's the number of protons, and that's what you have to give. Okay. There are some questions here. These are just for you to test yourself. If you weren't sure about this, these questions on the slide let you just check. Okay, are you actually able to do this? Okay, so the atomic number is this one down here. It's the small number. The mass number is this one up the top. It's the bigger number. Number of protons is 16. Number of electrons is 16. And the number of neutrons is the small number taken away from the top number. If you're unsure, you can then practice that on some other ones. Up the top, this says this is optional practice. That is for you. If you weren't sure about this, here is a practice for you to try. But I'm hoping that our higher level students who have taken a C1 paper before Christmas and have been revising are able to work out the number of protons, electrons, and neutrons in an atom. So now we get on to talking about something else, isotopes. We need to talk about isotopes because it's really difficult to talk about radioactivity without talking about isotopes. And I'm hoping that lots of you remember the definition of an isotope, which is what we've got here. Okay, these are all isotopes of oxygen. And what we can see is that they all have the same number of protons because the atomic number there is 8 for all of them. So they all have the same number of protons, but their mass numbers are different. If they've got the same number of protons and a different mass number, that means they must have a different number of neutrons. And that's the definition of an isotope. Okay, so this one has 8 neutrons, 16 take away 8. This one has 9 neutrons, 8 from 17, and this one has 10 neutrons. It has to have the same number of protons or it wouldn't be oxygen. 8, 8, 8. Protons are not different. So an isotope is a version of an element that has the same number of protons, but different numbers of neutrons. That is the definition of an isotope. Okay, a radioisotope that we're going to talk about in a minute is an isotope, any isotope that is radioactive, so that undergoes radioactive decay. And we're going to talk about that in a moment. Okay, so there's the definition. I put it in red so that you can be absolutely clear that that is the definition. That is a flashcard. If you didn't already know that absolutely off the top of your head, and I'm aware that a lot of people do, that's your definition. That's your flashcard there. Okay. Now, down the bottom in really big red letters, this is not a requirement this week. Those questions, those are for you to test yourself. Okay. Can you answer these questions? If you can't, go back, look at the slides, just make sure that you're able to answer those questions, because that then helps us do the next bit. Okay. So let me talk a little bit about the work. I'm going to be really careful with the time today because I really want to do a Kahoot as we get a little bit further through this. Didn't mention that. If you have your phone handy, that's going to really help. Or you're going to need to open another tab when I say let's do a Kahoot. So I'm going to test you on this towards the end of the webinar just to see how people are feeling about it and also to have a bit of interactivity. Okay. The work for this week in your Google Classroom, these slides are in the classroom. Now, we've been listening to the feedback, 520 people filled in our feedback form. It was great. And one of the things that you've asked for is for things to be much clearer and much more separate in your classrooms. So the slides for reading are called slides to read and revise. That's these ones. There is then another set of slides called written questions. So those are the slides where, and I've taken all the questions out, put them on a slide so you can just answer them on those questions. And then there are 3 quizzes, one on density, one on the particle model of matter. So you can test, do I need to revise this or not, or do I actually already know it? Okay, for both those, and then one on radioactivity, which is what I'm doing now. They're all much shorter than some of the quizzes that you've done before. So it allows you some time to do some revision as well. Okay. Right. So again, this was something that's in C1, so I don't have to go into this in a huge amount of detail, but you have to be able to remember the plum pudding model. The idea that we had this big ball of positive charge, that's this gray fuzzy bit here, a big ball of positive charge, and stuck in it, like raisins or plums in a Christmas pudding, we had these electrons dotted around. Seemed great. J.J. Thomson came up with it. He had a nice tash. In fact, all of these people, I think, had quite impressive moustaches, bit irrelevant. But then Rutherford came along, and Rutherford fired alpha particles. We're going to talk about them in a minute, but they're heavy, okay? They're big, heavy particles, and he fired them at gold foil. He chose gold because you can hammer gold out until it's only a few atoms thick. Gold leaf that you see sometimes on food is only a few atoms thick. They've also got a positive charge. And he expected them to go straight through the particle, to be sort of smashing it to pieces, but something different happened. Okay, something very different happened, and he got 3 different things. And you need to know these 3 things from Rutherford's scattering experiment. Some of the particles, in fact, most of them, went straight through. Nothing happened. They didn't get deflected. They didn't bounce off in different directions because they'd hit something. They just went straight through. Quite a lot of them had a massive deflection in their angle, 30 degrees. It was really quite a significant deflection. And then a very small number, but some of them bounced back. And that let him come to 3 different conclusions. If most of them go through, most of the atom was empty space because they hit nothing. They just carried on in a straight line. Where they were deflected through a large angle, that meant something was positive. There was something positive in there because they're positive particles and they got deflected away from it. And if they bounced back, something in the middle was really, really quite massive. There was a massive concentrated bit of mass that was very small because these heavy particles bounced. And so he was able to come up with the nuclear model of the atom. Nuclear. See where we're going there? So we've talked about radioisotopes, the nuclear model of the atom. We're talking about the nucleus, and we're into radioactive decay. There you go. So this is the bit that I really want to focus on. I really want to focus on what we mean by radioactive decay, being able to describe alpha, beta, and gamma decay, and also to be able to talk about half-life as well as nuclear equations, because all of these things are actually easy marks in any exam or assessment that you had. But you do need to make sure that you know it. So here's a quick true or false. What I'd like you to do is just take a moment to read that. And, you know, I'm not asking you to type it in the chat box or anything, but just to yourself, just decide whether you think these things are true or false. Can radiation mutate you, giving you a deformity? We'll have a true or false for that. Sleeping next to someone most nights for a year results in a radiation dose about the same as an X-ray of your hand. Shipment of 1.5 tons of plutonium had the energy of about 1,000 oil tankers. Chernobyl, if you've watched the series, deformed farm animals, true or false? Fruits and vegetables causes more deaths being flown from other countries than the transportation of nuclear waste. And when an object is near a radioactive substance, the radiation is absorbed. So I hope you've had a little think about that. And then let's just run through true or false. Radiation can't mutate you, giving you a deformity. That can't happen. It causes mutations at cellular level, but it can't suddenly deform you. You can't turn into the Hulk. That didn't actually happen, nor could you turn into Spider-Man. Both of those things are examples of that happening, and I'm afraid it didn't. Otherwise, I would be deliberately getting bitten by radioactive spiders all the time. Sleeping next to someone for most nights does actually give you the same amount of radiation as an X-ray from your hand. Okay, so I am giving out radiation all of the time because of the things I've eaten, because of what I breathed in. There's an awful lot of energy in plutonium. 1.5 tons of it is the same as 1,000 oil tankers. There are no deformed farm animals from Chernobyl. And before someone says, but Facebook, the internet, they're all fake news, I'm afraid. There were not deformed farm animals born as a result. The transportation of fruit and vegetables will cause more deaths over the next 20 years. So the aircraft and lorries involved in transporting it will cause more deaths through air pollution than the transportation of nuclear waste. And something can't become radioactive by being near a radioactive substance. It could be damaged, but it can't become radioactive. So types. We need to define 2 different words. So radioactive decay is the process of a radioactive atom emitting radiation. So it breaks down, it decays, it breaks down, and it gives out some radiation. And activity is the rate at which it decays. Okay, so it's the rate at which it decays. So the radioactive activity is the rate and decay is the process. Okay, so let's talk about our types. Alpha. Now, alpha particles are great. 2 protons and 2 neutrons. So I'm just going to switch cameras for a second. And we are going to have a look at our alpha particle. So for our alpha particle, what you might notice on this, or you might have noticed on the screen, was we've got a nice Greek alpha like that. Okay. And what you might also notice next to it is that we've got 4, 2 like that. And what that's telling us, that's its mass number, because it's got, remember, it had 2 protons and 2 neutrons. So its mass is 4 and its atomic number is 2. And sometimes we draw it like this. So we've got 2 protons and we've got 2 neutrons. So that's an alpha particle. It is essentially a bit of nucleus. Okay, it's a helium nucleus. It's got a charge as well of +2. It can't get very far. It's a big, heavy thing. We can actually stop it with a couple of centimeters of air. Where's my camera gone? A couple of centimeters of air or a piece of paper. Okay. And so everyone goes, well, it's not actually that dangerous then. It is. It's extremely dangerous because it's such a big, heavy particle. It's very ionizing. And remember at the beginning, I said we were going to talk a little bit about ions. I'm hoping you remember from chemistry that an ion is an atom that has lost or gained an electron. So that big heavy particle can come lumbering along and knock electrons off and ionize things. Ionizing radiation is what is dangerous and harmful. That is what can lead to mutations and cancer. Okay. The reason that alpha doesn't harm us is it can't get in. It cannot get inside us because it can't even get through a bit of paper. If it did get in, it would be a problem. And it has been. Any of you that know the story of Alexander Litvinenko? If you don't, I'll tell it to you another time. Then we've got beta radiation. Now, beta radiation, okay, a neutron turns into a proton and gives off an electron. Okay, what you really need to know about it, again, I'm going to switch my camera around here like this, okay, is being able to write it like so. So we give it the Greek symbol again, Greek symbol beta, like that, and we give it a naught at the top because it has no neutrons and no protons, but okay, a neutron turns into a proton. So we just give it down there -1, a neutron turning into a proton. And I'll explain all of that later. Okay, so it's quite important that you know these symbols. It's easier to harder to stop. It can turn into It can get through everything except a thin bit of aluminium. Okay. Now, gamma radiation follows on from those two. So those two are physical things. Okay. An alpha particle is a thing. It's big, it's heavy. Okay. 2 protons, 2 neutrons. A beta particle is a neutron churning into a proton and an electron being given out. There is a particle. Okay. It's only a little particle. It's much faster though. Gamma is a high energy electromagnetic wave. Hopefully, you know your electromagnetic spectrum. You've got radio waves and microwaves and visible light and ultraviolet and X-rays and gamma rays. Gamma rays right at that end. Very high energy electromagnetic wave, speed of light. It can only be stopped by thick bits of lead or concrete. Okay. However, it's not very ionizing. We describe it as highly penetrating. Alpha particles are not very penetrating. They can't get through paper. They can't penetrate paper. Gamma radiation is. Gamma radiation would go all the way through you, very penetrating, but not very ionizing. Okay. However,
So,
hello, Miss.
hello, sorry. It seems like some are having issues seeing the switch between cameras.
Oh dear. Unfortunately, I don't know what to say there. It may be a setting on their feed. I will try and not use it too often. Right. Okay. So let's just talk about penetrating power. Alpha, there's our alpha, can't get through paper. Beta, stopped by aluminium. Gamma takes a few centimeters of lead or a lot of concrete to stop it. That's penetrating. Okay. Now we've got to talk about being able to detect radiation. And what I really want to get into, so I'm going to move a little bit quicker, is talking about radioactive decay and how we write the equations for them. Okay, so detecting it, you need to know we use a thing called a Geiger tube or a Geiger-Müller tube, and it's able to detect, okay, the ionization essentially that is coming from the radioactive decay. Okay, so alpha radiation has the greatest ionizing effect. Okay, and gamma radiation has the least ionizing effect. Okay, ionization is the thing that causes mutations such as cancer and can damage cells. Now, just to make sure that you've been awake during this, I am going to so there's the dangers of radioactivity. Just going to click through this. Now, optional revision task, and it's key. Optional revision task. Okay, if you're not clear, if you couldn't already write out alpha, beta, gamma, what they are, write the symbols, describe them, talk about ionization and penetrating power, you need to make a revision resource on that. It's optional, but you need to know those things. Okay, just going to see who was awake at the beginning. This has all been me talking, so let's just check if you can remember this. Which number on the periodic table is the number of protons and neutrons added together? Swap my boards around while we're doing that. Fantastic. So most of you knew it. Okay, it's the mass number. It's the number of protons and neutrons added together. Those of you who didn't, you do need to go away and learn these definitions. They are really, really important. Okay, so the correct answer was mass number. Let's just have another quick question, see if you were awake during an earlier part of it. So Rutherford, what type of particles that I've just talked about did Rutherford use to fire at the gold in his scattering experiment? Brilliant. 10 seconds in, quarter of you have voted. Keep going. Come on, I want everyone. That's half of you. Another 15 seconds. That'll do. Okay. And the majority of you were able to remember that that was alpha particles. Fantastic. Okay, excellent. Good work. Right. So now we get into about 10 minutes of me talking about how to do this. Now, these quick questions, again, because they're on these slides that are to read, this is not something that I expect you to answer on the slides. This is just for you to get your mind in the right place. Now, I am going to switch cameras. Now, if that's a problem, if you let Miss know, I would like to know how many people it's a problem for, but it should really, the settings should be allowing the majority of you to see that. I'm aware on some devices, perhaps, it won't change the view. But what I wanted to talk about was this, because if we can't do this, the next part is a little bit difficult. So it said how many protons and neutrons in this. Okay, so how many protons is the bottom number? How many protons is the bottom number? So this has 90 protons. How many neutrons? It is this number here at the top, take away the number underneath. So this has 138 neutrons. Okay, if I was to take the next one down, it was 99 and 43. Okay, doesn't matter what the symbol means, irrelevant. How many protons has it got? That's the bottom number. It has 43 protons. How many neutrons does it have? That's the top number. Take away the bottom number, so that is 56. Okay. You're allowed a calculator in your exam if you're unsure. So hopefully, as I go back to the other one, you can now see what I was doing there as I went through those. You just need to be able to do that. And there were some practice questions at the beginning if you weren't sure, because otherwise you aren't able to do these. Okay, so here is how we do radiation equations. And on the written questions are quite a few of these for you to look at. The first one up here is alpha decay. So if an atom decays into a new atom and emits an alpha particle, what we do is we take the alpha particle away from the top over here. You will never be expected to work out what symbol turns into what symbol. You might have to look it up on a periodic table, but you won't have to remember it. So radon here with 219 as its mass number, if we're taking an alpha particle away, we take 4 off the top. It had 86 here, an alpha particle has got 2 at the bottom, so we take 2 away. So we quite literally take away the 4 and the 2 from our first two numbers and write them here. So we have 215 and 84. I'm going to show you another example in a minute.
Sorry to interrupt.
That's okay.
If they click on view options, which is at the top of my screen, that fixes their camera issue and they can look at the camera.
Brilliant. Thank you, Miss.
Thank you to whoever told me that in the chat.
Right, that means I can go back to doing these written on here in a second as well, which makes it a little bit easier. For beta, all you actually need to remember, those of you that are better at maths will know this anyway, but again, we're taking away, so we took away an alpha particle, so we took 4 and 2 off. Here, we're taking away a beta particle, so we're taking away 0, well, that does nothing, and we're taking away -1. And you'll all know if you take away a minus number, you add it. So take away -1, it means add 1, so 6 turns into 7, okay, because a neutron turned into a proton. So what we have a look at some more of those, okay, and I will do them on this bit of board over here. So I'm just going to move my board up so that I can get it, and hopefully you can now all see that screen. So maybe if you've got a piece of paper, you could write that down. I'm going to write it down now, okay, and then I am going to show you how I would do it. Okay, so I'm going to stop sharing because I've written it down, and I'm going to use a different camera so that you can see this nice and big, I hope. Fantastic. Okay, so that's where I got to before. So it had 226, 88, and it decayed to make radon plus an alpha particle. It said, well, alpha is 4, 2. I knew that because I've learnt it. Okay. And that means I take 4 from this number. So it's 2, 2, 2. And I take 2 from this number. So that is 86. And that is my answer for 2 marks in the exam, because I knew alpha was 4, 2. And what looked like a difficult question, actually, I hope wasn't too difficult. Let me go back and share my screen, and we'll look at the beta one. Okay. So here is the beta one underneath. I'm going to turn my board over. Okay. And so it says I've got 13153 iodine, and that's decaying to make, doesn't really matter, xenon plus a beta particle. Now, as long as I know what a beta particle is, I can do this really easily, because it's, I'll do my beta symbol, it's 0 minus 1. Well, I take 0 away from 131, it's 131. I take minus 1 away from 53. Remember, take away a minus number is the same as add it, 54. There we go, for 2 marks in the exam. Okay, as long as you remember those things and you just take them away each time, that will give you the correct answer. These questions are in your written answer slides, so you don't have to do them on this slide, but there are quite a few radiation equations for you to do in those questions. So we have 228 and 90 with alpha decay and so on, and then we have some beta decay questions. You should be able to do those, I hope, if you've watched this or you watch it back again, because those are lovely, easy marks in the exam. Okay. Now, half-life. How long have I got? Yep, I have got time to talk about half-life. Didn't want, if it goes too quick, I'll just put it in next week's. Okay. What I'm not going to do is rush to get through it, but I'm going to see how far we can get through. So half-life is a nice, simple idea. It is the time it takes for the count rate or the number of nuclei to halve. So if we look at the top of my graph over here, at the beginning, day 0, right now, we have 80 counts per minute of this substance. Doesn't matter what the substance is. The half-life is how long, a half-life is a time, how long it takes to half. So if it was at 80, I go down to 40, because that's half 80. And I go across 2 days. The half-life of that substance was 2 days. Now that means that that should always be true. So it should take 2 days to half next time. So I can check that, 40 to 20. Let's go across 2 to 4. It took 2 more days. It's completely correct. Okay. The half-life of the substance, here's our definition, the time it takes for half of the particles to decay, or the time it takes for the count rate to decrease by half. Depends what they give you on the graph. It is essentially the same thing. You half it. Okay, it is the time it takes to half it. And it allows us to do all sorts of calculations. So we just did that one, but well, hopefully. No, that's not the one I was looking for. Whoops. I thought, there are some more questions. I remember I put the questions. That's why I've taken them out. I took them out and put them in your written, I put them in the written answer section. Describe this, draw this graph, describe and explain what it shows. Okay, so I'm going to have to go back, because it would appear that the axes of those have disappeared off here in the translation into these slides. But it is essentially asking you the same question as this one. It is showing you the time, the number of counts against time, and you're able to work out half-life by working out how long it took for it to half. They might ask you to do it in a different way. They might say the half-life is 2 days. What would the count rate be after 6 days? But you didn't have a graph. Well, that's easy, because you just half it until you get to 6 days. If the half-life is, I'm going to use my other camera. If the half-life is 2 days and you start with 80, okay, we know that after 2 days, you will have 40. So after 2 more days, so 4 days in total, you will have 20. They said after 6 days, so that's another half-life. So 2, 2, 2, you'll have 10. Okay, we can work that out because we just work out how many half-lives fit into 6. 1, 2, 3, because it was 2 days. And so we go through 3 half-lives. 1 half, 2, 3. We're down to 10. Now, if you're not comfortable with the maths, I always suggest to people that they lay it out like this. Okay, that you write out the number and it says, right, after 16 days, how much would you have left? Well, that would be 8 half-lives, and you just go through and halve it 8 times and write that number down. Okay, it takes a little bit of practice, which is why there are some questions in the written answers for you to try working out some half-lives or working it backwards like that. Okay, now, so I will go back and fix this in the classroom. Okay, radioactive contamination, there's just 2 things that are important here. Okay, is that you understand the difference between radioactive contamination and irradiation. Okay, radioactive contamination is the unwanted presence of materials containing radioactive atoms. That means there is something radioactive. I'm doing all sorts of hand gestures now and you can't see me because I haven't swapped my camera back. Right, it's something containing radioactive material that's somewhere you don't want it to be. The radioactive material has got somewhere, not radiation, the material has got somewhere. Okay, now the risk depends on what type of radiation it is. If you've got some alpha radiation on the table, okay, the risk isn't huge unless you touch it and eat it. Okay, which type of radiation would pose the greatest risk to health? Probably gamma radiation. Would it be? Because it can go through people, or is it alpha radiation? Because if someone ingests it, it's going to cause them significant harm. Okay, particles, alpha particles, are a huge problem. How will the half-life affect the level of risk? Well, if the half-life is 10 seconds, then obviously that radioactive material, there will be such a small amount of it after only minutes or hours that it would no longer be harmful. If the half-life is 1,000 years, then that radioactive material is going to stay around for a very long time and cause a problem. There was a very good question a few years ago about Marie Curie's notebooks from her lab and why they are still dangerous. And they talk about the half-life of the materials that she was using and the fact that it was only 140 years ago. The half-life is 1,000 years. And so her notebooks are still covered and contaminated with radioactive material. It's a very interesting question. Irradiation is something completely different. Irradiation is where you deliberately expose an object to nuclear radiation, that's alpha, beta, or gamma, for all sorts of reasons. But the object does not become radioactive. You take the source of radiation away, it stops. There is no more radiation there. It does not make it radioactive. We use it to clean surgical implements. And we also use it to preserve food. Strawberries are very commonly irradiated with gamma radiation, which is why they keep longer on the shelves. Strawberries shouldn't keep for a week in the fridge. Strawberries, if you go and pick them off a plant, will keep for a day or 2 at best. But irradiated, they will last much, much longer. Okay. Now, I'm hoping I've got enough people here still to try a little bit of a quiz about this. I'm just going to have to stop sharing and then start sharing again. Okay. Hopefully I've still got it here. Fantastic. And now, okay, so bit of a Kahoot. I love a bit of a Kahoot, but it also is going to allow you and me to see how you're doing in terms of your understanding of the radiation that we have talked about today. So you need to get your phone. If you don't know how to do this, you just go to kahoot.it. And then type in that game pin. Now, I've did this with year 10, managed to have 45 people playing at once. If you write anything rude, I will just kick you out and I won't wait for you to rejoin. It would be really good if we could have at least 20 people. It's fantastic seeing lots of people that I know are in my class, which is really helpful. I love this music. Makes me very happy. Right. I wonder if I can... Right, I can't wait too long because I'm really acutely aware of the fact that we have 9 minutes left. Now, if you're watching this as a video on catch up, if you like, it's still worth watching this and shouting the answers out, because this tests, do you remember what you need to know about radioactive sources and radiation? Okay, it was a bit of a whirlwind tour. The thing that I hope we went through the most was radioactive equations. There are lots of those in the questions. Please don't forget to watch the videos about density and the particulate model of matter. That's really important. And alpha, beta, and gamma, penetrating and ionizing, very important words. I am going to start it in 25 seconds. We've only got 25 people, but the rest of you that aren't taking part on screen, maybe you can just watch it go past and see if you know the answers. There's 10 seconds of those 25 left. I don't want to let it run on any longer, or we will get kicked out of it when the next person starts their Zoom. So let's get going. So let's have a look at some of these questions about radioactivity. I'm sorry if it hasn't let you join, but you can still answer the questions as it goes past. Alpha particle is made up of. We've drawn it. I've talked about it. I'm going to skip it. I'm going to skip it. No, I'm not. I'm going to let you have all the time for that one. Excellent. 2 protons, 2 neutrons, helium nucleus. Fantastic. You need to know that. Not so sure that I approve of that name that's winning, but we've started now, so I hope it's just your Austrian heritage. Which material can block beta radiation? I'm going to skip it. Aluminium. Fantastic. Thin piece of aluminium. Excellent. Lewis at the top there. How many of the nuclei in a sample will decay in one half-life? How many of the nuclei decay in a half-life? Good. Excellent. Half of them decay in a half-life. That's what a half-life is, the time it takes half of the nuclei to decay. Excellent. We're doing quite well here. Which is the most ionizing form of nuclear radiation? Excellent. Good. This is exactly the sort of thing we were looking at and the sort of thing you have to remember. Why is this one the most dangerous if you eat it? Fantastic. It's alpha because it's the most ionizing. Gamma is a bit weak, but it's more penetrating. I hope that's not the next question. It suddenly occurred to me. What can ionizing radiation do to cells? It's one important thing, and doing this can lead to cancer, because cancer is essentially a one of these. It's not orange. I'm glad no one picked that. It can mutate them. Okay, and I see why people cause them to multiply quickly, because that's what cancer is, but it's mutated cells that are multiplying quickly. Its mutation causes it to do that. What fraction of nuclei in a sample will have decayed after 2 half-lives? Oh, that's clever. Okay, so you've got a whole one, you've got 1 half-life, you've got another half-life. How much has decayed? And I know what people are going to get caught out with here. Good. Lots of people didn't get caught out. 3/4. I knew people get caught out with a quarter. Quarter's what's left. You're quite right. You go a half and then another half, you've got a quarter left. That means 3/4 has decayed. Okay, bit of a trick question there, but well spotted by quite a few people. Very pleased. Okay, so which is more dangerous? A contaminated sample of material or an irradiated sample of material? Really important you know what those 2 words mean. Good. Okay. Contaminated. Contaminated means we've got radioactive material somewhere we don't want it, and it's dangerous because people could ingest it, it could get into us. Irradiated doesn't stay radioactive afterwards. Okay. Strawberries are irradiated, they're safe. Okay. I promise they're safe. You don't have to stop eating strawberries. Okay. We might not get through all 25 questions, but this is good. What does a mass number tell us? Good, going quite fast. I'm going to skip it in a second. Good. the number of protons and neutrons. Now, if you're getting these wrong, what you need to be thinking is, I need to go away and revise that. And perhaps this week's work is actually you doing some revision on this topic and then sending that, for example, if I teach you, sending that to me and saying, actually, sir, I didn't know it, so I went back and revised it rather than doing all of the questions. What's the proton number tell you? The proton number. Saying it again. I'm going to skip it. Oops. Oh, right. Yeah. Miss one still. What's the relative mass of an electron? Now, this is a bit tricky, really, because I told you the real number and then I told you what we say.
I think I just got it wrong, sir. I think I just tapped the wrong one.
Oh, no. Okay.
Yeah, I did.
The actual number is 1/2000th. Okay, we do write 0, and we're okay to write 0, but the actual number is 1/2000th. Oh, Lewis, miss hitting the wrong button. What material is required to stop gamma radiation? How are we doing? We're doing okay for time. We've got 3 minutes left.
Sorry, I don't get to play very often, so I'm quite.
Let's skip. Let's see if we get more questions in. Good. Most of you could remember thick lead. We're gonna scoot on nice and quickly now to see if we can at least get to 20 before I have to stop. Which of the following half-lives would be best used as a medical tracer? Now, this is a common question. What you need to think about is, how long do you want it to stay in the body for equipment to be able to pick up the issue? Okay, and then I'm going to explain why. This is a really good question and a common question in your exams. Which would you choose?
Again.
Now, 5 hours. The reason we choose 5 hours, 4 seconds and 5 minutes are too quick. You don't, if you've ever gone to hospital for something, they don't see you 4 seconds or 5 minutes after you get there. Okay. However, if you go in and they give you a meal and say, right, we'll see you in an hour or two, if it hangs around for 5 hours, that's going to be brilliant. 2 weeks, that's risk of harm. We don't need it to stay for 2 weeks. So the answer is always going to be something that stays for hours for a medical tracer, always. Okay, there you go. We learned something extra as well I didn't have in my slides. I reckon in the time we've got, all elements must have the same number of, all atoms of the same element have. I mentioned this when I talked about oxygen isotopes.
I'm also demonstrating, sir, that you should read the whole question because I'm rushing, and then that means that I'm not getting the right answers. It's a valid point. Take your time.
However, protons, good. This is going to have to be the last question. I've got 1 minute until the next person is starting their webinar on this account. Okay, so last question. After this, I will press end game and we will have a winner. An isotope has. Brilliant. Right, so end the game. Let's have some winners.
Sorry.
Miss Wonstel, read the question.
Yep, read the question, take my time.
Adolf and Lewis. Fantastic.
Bye, Lewis.
Well, what I have to say to all of you is I hope that webinar is a nice mix of scientific information, a few worked examples, and something that's fun, but also to test yourself. I hope you find this week's work the same, that there is information to read and videos to watch. There are written questions to really get down into, do you know this? And there is Google quizzes just to, do I need to revise this or not? I reckon I know this. Do I? Do the Google quiz. You get 25 out of 25. You're kind of done on that topic, aren't you? If you get 6 out of 25, you probably need to be going away and doing some revision on it. If you do particularly well on one area, use that, the written questions to test yourself. Okay. I hope that's been good. If there are any questions, we're around for probably about a minute until the next person has to start their webinar. Otherwise, it's been great to see you. Don't forget that when you get an email saying you can come to school, there will be some science things out for you, particularly if you're in D&T sets. Fantastic. Thank you very much, Miss Wonstel.
No worries. Thank you for letting me play.
No, yeah, definitely. You're welcome. I've tried to get Cahoots. I'm aware there's still people here and they're listening to us just having a chat now. But I've tried to get Cahoots into all of them at the end because it's a nice way to find out if people understand. And it's also a bit interactive.
Mm.
I'm going to try and get some more things in after half term. But thank you for joining me, Miss. You're welcome to any of them. All right, bye everyone. I'm going to end it now.
Bye bye.
See you all.